Got a camshaft chain tensioner on sale.
Like, it's like you're planning to build a solar powerhouse or something. You planning to put some solar in your place?
Yeah, I have a solar panel.
Yeah, like,
Yeah.
you get money back, or how does it work?
No, I don't get money back.
It's about cheaper now.
Yeah, it's just cheaper. A little bit, yeah, cheaper.
How long does it? How many years will that take to pay off the solar?
I think it's about. They figure it to be about 17 to 20 years when it pays off for itself. Yeah. Yeah, very interesting.
It runs your whole house and everything?
Yeah.
Well, let's see if I can show you my latest flying video. Just got this today.
Oh, I did a plane the other day. That landed on Ruffin Road. What caused that one to crash?
Oh yeah, what happened to the Montgomery field accident? Did you hear what
Oh
happened?
my gosh, yeah. I just saw a boat. I just saw a boat version of this the other day.
Okay, you guys ready? Watching it?
Yeah.
I'm watching it.
It's a Jeep or something.
Did it lift the whole?
Can you explode the picture?
Side by side?
That's fucking sketch, dude.
I think we need some lift. Whoa!
Oh,
Jesus Christ.
that's a failure. That's a failure.
I don't know if that was fake or not, but
Yeah, I would have taken my chances.
No, I saw a boat version of that exact same thing.
they tried to video.
Yeah.
Oh well.
You should have ejected.
Yeah, I don't know that.
Who constructed this?
Yeah, I'm not sure I would fly that.
How do they steer? How do they steer that thing?
That's a good question. Obviously not well.
They didn't.
The nose up part, they didn't get down so well. All right. So just very briefly, we've talked already about batteries, electrochemical. The battery, we use the term primary for a one-time use. Primary cell, secondary cell means it can be charged and recharged and again and again, not indefinitely, but for certainly a substantial number of times. That's probably one other area in battery technology that we're going to see some advances in. They'll get better and better at making a battery that will last a lot longer.
Instead of
And the truth is,
5 years of.
well, if you think about it, if we could get it to where it lasts, say, 10 years, the battery would last 10 years. That's going to be more than the lifespan of most cars. Okay, so then you don't need to recycle the battery multiple times during the lifespan of the car. Just whenever the car's done, it's all worn out.
Environmental impact that way.
Yeah, yeah. So less cost, less operational cost, more economically feasible. So we're going to see that, probably see that change as well, just because there's economic pressure to do it. We very commonly will use batteries for starting systems, and then if it's a very small vehicle, we sort of run everything DC. All bigger systems, we only use the DC electricity for the starting. So airliners, ships, etc., we either use DC to start them, or we use DC to start the APU, and then customer air coming off of the APU, or hydraulic power coming off the APU to start the main engines. Okay. Now, my guess is in the big ships, yeah, they do have batteries, and they do have DC power for starting the starting all of their big engines, electric engines. The other thing the battery does for us is this is what the generator looks like if it's charging on its own without a battery in line. If I put the battery in play, now you see when the thing first turns on, it gets a very sort of and then a little bit here, and then there it stabilizes out. You still see a little bit of the ripple, but for the most part, that battery absorbs all that variation in current. Okay, so the battery is a huge buffer, very much like a capacitor would be in the same situation. Okay, in fact, a capacitor might eliminate that to the point that I could run one capacitor that got rid of the bigger bumps, and then a higher frequency capacitor that got rid of all the little bitty wooferdills there as well.
Makes it smooth then.
You can make it very smooth if you wanted. Now, if you don't need it because it's not causing you a problem, you wouldn't waste your time doing it. Time, money, weight, etc. Okay, another place that you might see in an airplane that the battery will make some use of is occasionally you've got some high power users other than the starter, like the landing gear, okay, or a flap actuator or something else. So as that comes on, particularly landing gear up or landing gear going in the direction against the wind, fair amount of load, okay, hydraulic power pack comes on, something like that. Then you might see the battery also being a pretty good buffer for that. You guys, and I think we talked about this in batteries, but in your backup power systems for computers, they use the battery not only as the backup power source, but also as the buffer, along with a couple of big capacitors, to absorb any spike energy coming in, or if a lightning bolt hits the line coming in, etc. They use a big battery for that. Okay, another fairly recent technology is the hydrocarbon fuel cell, and they've got a fair number of these that are in play as backup delivery systems. In fact, I can't remember the name of the company. There's a company over here in Rancho Bernardo that did a whole lot of early work for Daimler, Mercedes-Benz, and General Motors, sort of early on, kind of doing some initial investigatory work. The idea here is if I create a membrane that a proton can travel through, or I really shouldn't say a proton, the atom in an ionized state, a positive ionized state, where it's missing an electron, it will travel through. In fact, it's inspired to travel through the membrane and come over to this side. Well, now this side becomes all very, very positive, and the electrons that are left here will travel through our circuit and come back here and rejoin with the atom. In fact, a chemical reaction will occur, and the hydrogen will form with oxygen in the form of H2O. Where the hydrogen comes from is a reformer device that takes methane or alcohol and strips the hydrogen out of the carbon, the hydrocarbon molecule. The carbon molecule is combined with an oxygen or with two oxygen molecules to form carbon dioxide. Hydrogen forms with water, which produces, or with oxygen to form water. Well, that's the same byproducts you get in the combustion process, right? If you get full, complete, perfect combustion, or partial combustion, it goes into the catalytic converter, what comes out?
CO2 and water vapor, right?
CO2, water vapor, and whatever else is in the air. Nitrogen.
And
Yeah.
trace
Okay.
elements.
So this does the same thing, only there's no boom, there's no bang, there's fairly limited heat production. You just pour fuel in and electricity comes out the other end. We're not there yet, but boy, those would be kind of cool. I could make a whole bunch of those that are really lightweight. I could just put those throughout the wings of the airplane, sort of with the fuel tanks surrounded around them, and little electric motor up front. Zoom, 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 away we go. Ain't it grand?
if they were using electricity and all that, is it gonna be going back to having propellers on the end? I mean, we're no longer.
Well, I would still have an electric,
Right?
I would still have an electric motor
Right.
driving the propeller to make the airplane.
That's what I mean, is
Yeah.
it going back to these planes are gonna have propellers sticking out like they used to, right?
Well, or ducted fan,
Okay.
probably ducted fan. We've done some pretty neat development technology,
More
actually in the
efficient
model
than just,
world, with ducted fans. But,
just a propeller sticking out in the wind, the ducted fan works much better, right?
depending on what you're doing, yes. I can tell you though, a single bladed propeller is pretty darn efficient. The problem with the ducted fan is you gotta pay for the weight of all the ducting.
Okay.
Okay, so the solar voltaic cell, this is, I truly do believe that, maybe not in my lifetime, but some of your lifetimes, you're gonna see us in a place where a big percentage, if not more than half of our energy, comes from photovoltaic sources. Okay, it's just there is so much heat energy, light energy, hitting the surface of the planet that we don't make use of. And if we could get to the point that we can directly make use of it through something like this, photovoltaic cells, without it being too toxic or, what other, bad ramifications, then we're gonna go down that rabbit hole. I think the other thing that will go along with this is we'll become more and more efficient at using the electricity. Okay? And that's certainly been true. Look at the little electric motors that are out nowadays compared to 10 years ago, or 15 years ago. They've got little electric motors that are that big around, and they'll drive your car down the road at a snappy. Okay, they've got one of those on each wheel, and I mean it's 0 to 60 in now. They go really, really well. And they're small, little bitty, lightweight motors compared to, not that long ago. So I think that's another area. We're going to see both of these becoming more and more prevalent. Now, what would be really cool would be able to build an airplane with enough of these on the surface of the airplane, and they're effective enough to pull in enough electricity to keep you cruising to where you didn't even need any additional, right? Maybe you've got a battery on board to take off and get going, but once you get above the clouds, all the solar panels are now doing their thing. They recharge your battery and they carry you from point A to point B. That'd be really, really cool. Okay. Again, you're going to see some of this happen in the small airplane world. I don't know if how well it will work, at least early on in the big airplane world.
You'd be limited to only flying in the daytime.
Yeah, but
Didn't they have that, the one that was cleared that flew around the world on solar, on the wing?
they've already done. I don't know if it did. Yeah, I guess it did make it all the way around the world. Yeah.
But I mean, it was really big, but I mean, it wasn't
It was
nobody.
a huge surface area, and it was a very high altitude,
Mhm.
and it was high, and they flew all the way around the world.
So they just lied, basically.
It's a big, huge
It had
glider,
propeller on it.
Gossamer glider.
Right.
It was, and if they hit any kind of weather,
Which is very efficient. It saved a lot of energy.
it probably would have torn it up. But
Probably what the reason for the high altitude was to decrease the weather.
okay, well, decreased weather, but more importantly, increased your
Airspeed.
yeah,
Thinner
increased your
air,
airspeed.
thinner air, that's right.
So, but again, this is a function of right now. This uses a very narrow band of light energy or of electromagnetic radiation. If we can double that, or triple that, or quadruple it, pretty soon each little panel is now producing 10 times of what it used to produce. Pretty soon it becomes viable. Okay, so now, yeah, you can charge your cell phone in a day. I don't know, that's already probably quite a bit better. I think, I remember the last time I looked at this was about 8 or 10 years ago, and it was a pretty good size panel. And it had to be bright sunlight for the whole day to get your cell phone charged up. they've probably got it down to smaller panels now, and it folds up nicer, and, yeah. So, and a cell phone isn't really a big power user, but still. The other big advantage of this technology is no moving parts. Keep it clean, don't let it get hit by lightning. It theoretically ought to last for a long, 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 long time. So, okay. Yeah, all right. I'm not going to talk about that until I come back and start talking about digital technology. All right, so AC theory. We've said the electrons go back and forth. In direct current, they only go in one direction, or they pulse in one direction. Now, the first thing we need to do is we need to figure out a way to model electron behavior. So we can use the Cartesian coordinate system. I think his name was Descartes. Now, how they get Cartesian out of Descartes, I don't know, but they did. And he was sitting on the floor looking up at the ceiling. And they had all these little squares, and he realized, you know, you could plot travel by using a line grid system. So we can plot travel of something by using a line grid system. So, for example, I could plot travel here. I could call this time, or I could call this degrees of rotation. Here on this scale, I could call this voltage or current. I could say positive or negative that way. Another thing I could do with the Cartesian coordinate system that's kind of cool is I could create a scale that goes this way and a scale that goes this way. We're going to call this y. Usually the vertical we call y, the horizontal we call x, and the one that sort of comes out of the board we call z. What I could do here is I could say from here is 0 and 0, and here we're going to go 100. Over here we're going to go 200, right? And then what we're going to do is we're going to say right about here, fresh water freezes. Okay. However, on our scale for here, we're going to say right about here, salt water freezes. But fresh water freezes out about here somewhere. Okay. We're then going to say right about here, salt water boils, but right about here, fresh water boils. And up here, we're going to say fresh water boils here. So if I go out to there and make a mark like that, I can now draw a line here. Okay. From that XY coordinate system, I can then plug that, and I'm not going to do it, but I can plug that into an algebraic formula and then reformulate that to come up with the formula for converting from Fahrenheit to Celsius, or from Celsius to Fahrenheit. Okay. The other thing I can do over here is if I want to start plotting motion, what I could do, remember I said time, so I could say, I get my voltmeter, where it is, I am the human voltmeter. I measure something. Okay, and I make a little X. Okay, 2, 3, 4, 5. Measure something. Okay, 1, 2, 3, 4, 5. Make another little X. Okay, 4, 5. Measure something. Make another little X. Right? I could do that over time. Or I could do it in terms of rotation. So I could say I've got my big magnet here, right? And I've got a wire, and I'm spinning the wire around in the magnetic field. Okay? And I could say, you know, maybe right there, since I'm getting no cutting up here, I call that 0, and then 90, and then 0, and then 90. So what I could do is I could say, you know, at the beginning point in 0 degrees of rotation, I've got no voltage. But at 90 degrees of rotation, I've got maximum voltage or current. And then at 180, I've got 0 degrees. And then at 270, I'm down here at minimum current, into the negative. And then back at 360 degrees, I'm back to 0. And what I would be doing is plotting the rotational motion in a Cartesian coordinate system, right? So if I take my Cartesian coordinate system, and let's say 100 is there, or 1, it doesn't really matter. If I plot my motion kind of around like that, what's going to happen is, in this particular case, I'm saying voltage is on that scale, and duration of rotation is on this scale. Well, the amplitude of voltage during part of the rotation isn't going to decrease very much. Then it's going to decrease a whole lot, right, over a fairly short period of time. So if I look at 45 degrees right there, I've rotated halfway around, right? So in terms of degrees of rotation, or in terms of time, if I'm at an even RPM, I'll have gone, you know, in this case, 1/8 of a revolution. However, my voltage, which I said was a scale right here, it's actually only right there. So my voltage has only dropped a little bit. It hasn't come down to halfway. It, in fact, has come down to 0.707, which is going to be the sine of 45 degrees. So what we're going to do is we can use this Cartesian coordinate system to model circular behavior, which becomes the mathematical field of trigonometry. Okay, now you guys probably played with trigonometry a little bit in general, but you probably did it in just straight unit circle. And what we're going to do is we can plot it like this, and what's going to end up happening is we're going to see that our electron travel goes from stopped, goes faster and faster and faster to maximum speed, slows down to stop, and then starts going the opposite direction. So it's going to go really, really fast, slow down, come to stop, turn around, slow, faster, 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 slow down, come to a stop. If it wasn't traveling in that circle and it didn't model that, instead we did like some kind of a linear function where, I don't know, something magnet went down a shaft and then came back up a shaft and then went back down a shaft, cutting across our wires. What we would probably end up with is something that looks, something that looks sort of very pointy, kind of like that, which would actually be very spiky. And remember that other chart I showed you, it would look really, really funky. On the other hand, if I actually do it with the sine wave, I'm going to sort of rise a little bit higher and then flatten out just a little bit right through here. Again, rise a little bit out. Same thing here, and flatten down that way and come back up. It's going to make it quite a bit less bumpy. To smooth things out. For this reason, if I can take my wire and put it in an arc and have it travel around through I don't know, take my big magnet like this, down like that, and have my magnetic lines of flux traveling through here, and I can get that wire to cut through and cut through and cut through. Then I can have this very, very, what's called sinusoidal AC wave. Now, this is going to work very much like a DC circuit, except we don't really know how to compare it to a DC circuit. So, what's the DC equivalent of this? Well, first off, the light bulb doesn't care which way the electrons are going through it, right?
Mm-hmm.
So we've said the behavior down here, it's going the opposite direction, but the light bulb doesn't really care. So mathematically, we can just flip it up here. It still represents the same amplitude, right? So we can just sort of flip that up there and put it right here. I didn't get it right. Yeah, right?
Okay.
We can then take, and whack off the tops right here, and then take those tops and put them in here, and put them in here, and fill everything up. Make it all real, real nice and fill. Okay? The value that we'll be at happens to be right at this halfway point in terms of rotation. Okay? Or 0.707 of the maximum instantaneous voltage that we reached right here. Okay? So the maximum instantaneous voltage is always, in AC, is always going to be quite a bit higher. However, if you take your meter, AC meter, and plug it into the wall, plug it right into here, it's going to give us some value. Shall we try it?
Mm-hmm.
Let's see if I can electrocute it.
Oh, shit.
Yeah.
Okay, what group is on battery G?
That's us.
Okay, if I fry this meter, I'm gonna blame it on you.
Okay, good.
Okay, let's see, volts. And I want the little squiggly line. Okay, I don't know that I can get all the way into here.
It's unplugged.
Oh, that one's unplugged. All right. And 122.6, 0.4, 0.5. Okay.
Step down for a second.
That's actually the DC equivalent. If you take that and divide it by 707, what do you get, Mr. Darcy? Come on, you got the calculator, go fast.
What is it?
What is it?
Take your 122 and divide it by 707, 0.707, or the sine of 45.
172.56.
How much?
172.
So yeah, about 170 volts. Okay, 170, and if you're at 110, it's 167. But that's your maximum instantaneous peak voltage, and your minimum is going to be a negative 170, right? And your peak to peak voltage is going to be 340 volts or 330 volts, somewhere in there. That never gives it to you. If you look in the manual somewhere here, doesn't say it on the screen. Better meters do say it on the screen. What they'll actually say is AC RMS. What they're doing is root mean squared averaging function to get to 0.707. So what they're trying to do is give you the DC equivalent. That's why this value that comes out of the wall, we say 120, 115, 110, we don't really care. It's approximately the DC equivalent. And the truth of the matter is, if I put a 200-foot electric extension cord on there, fire up my skill saw, and start cutting through wood, the voltage drop that's going to come across that entire length of extension cord is probably going to drop it down to 90 or 80 volts, right? So voltage is sort of a transient value. We create some preferred areas, 120 volts, 12 volts, 24 volts, okay? Something like that. So, wow, we're up to 123, 122, 129, 131, 100. Oh man, it's moving so fast I can barely read it. Well, that's where this plotting thing becomes kind of useful. Now I can start looking at that, and that'll be very, very useful. So when you look at an AC circuit, electrons are going back and forth. We've said electron movement in any matter, there is some resistance to it. That resistance doesn't change no matter which way the electrons are going, or even if they're going back and forth. That doesn't change. So with respect to AC, Ohm's law applies. Okay? The Ohm's law I had up here, it applies. Flat for AC resistance, Ohm's law applies. You don't have to make any modification to it. The same as DC. The problem is, we've said the current is constantly changing. And just a little while ago, I told you that inductors, particularly coils, don't like the change in current. Okay. Before that, I showed you a capacitor that said it doesn't like it when the current doesn't change. DC, it stops DC cold. One pulse and you're done. But if the switches, the leads are going back and forth all the time, the energy goes right through it. So it turns out that capacitors and inductors can impede the flow of electricity in a way that is not resistance. Okay? Now that doesn't mean that some heat is being generated somewhere. What it does mean is your nuclear reactor has to work a little harder if it's AC. And we got to compensate for that. And in fact, the faster we go, the worse it's going to get. Not because capacitive or inductive behavior. It turns out that the capacitive behavior can cancel the inductive behavior. The problem is most of our loads, particularly our big loads, are inductors. Okay? All the electric motors around you right now. Okay? All the coils and transformers and all of these lights. In fact, the only part of the load in these lights that's not inductive is the actual tube itself, which is actually capacitive. Okay? All the blower motors, the compressor, right? All the transformers are all big inductors. So the preponderance of circuits that we use are inductors, and inductors don't like higher frequency. Really, really don't like it. Capacitors do, but inductors don't. Okay. So, but it is so darn simple to make. So we're going to use it. It's very, very easy to change the power to whatever you want. I don't like 123 volts. I want 36 volts. Why do I want 36 volts? Well, because my arc welder likes to be at anywhere from 25 to 36 volts. Yeah, most arc welders are down around here. High current, but fairly low voltage. You need a lot of current. I got to make an arc. So I'll just kick it down to 25, 36 volts, somewhere in there. Okay. I might arc it in AC or I might arc in DC. Turns out, depending on different kinds of arc welding, one works better than the other, depending on what you're doing. Okay. I'd use a transformer. Not one of those things that destroys the city of Chicago. Okay. It's only in the movies, guys. I mean, I was okay with destroying the city of Chicago. Anybody that does that to the airport, they ought to be destroyed. Yeah. Okay. The other thing that's really, really, really useful with AC is it turns out that we can make a big splash in the realm of electromagnetism. Because it turns out that this energy exists everywhere. In space, in the sun, in the earth, in all matter. this medium exists everywhere. And so if we make a big electrostatic, electromagnetic splash, that will cause wave propagation outwards. And if we put meaning to that splash, to that information, then somewhere else we can listen to it or hear it and have transmitted. Okay? Anybody remember who the first person to try that was?
Graham Bell? Alexander Graham Bell? No.
The guy that sent the message all the way around the world. Marconi.
Okay.
Actually, one of the antenna stations, if you go up to, it's not, there's a Point Reyes, Carmel, not north of Carmel, Point Reyes, north of San Francisco, north of the Golden Gate Bridge. One of the big antennas, these things were like 400 or 500 feet tall. Long wave radio, they've got a whole, what do they call it, museum, and you can go up there and visit the site. I think it's free.
The big red tower or something?
The tower's not there anymore, but the big concrete emplacements for where the tower was mounted to are all there. Being ocean air, the tower rotted away years ago, but they had to knock it down. But they've got all the pictures and everything of it. I have no idea how much money they spent, but they sent a radio message all the way around the world. They had these antennas. Okay, so Ohm's law applies. Kirchhoff's laws apply equally in the world of AC and DC when we talk about resistance. But when we start talking about capacitance and inductance, we're now going to have, we're going to have to invent a new word, some imposition to the flow of that current. It's not going to necessarily cause the wire to get hotter, but what do the magnetic fields do as they come out of the coil or come out of the wire? What do they affect? Do they magnetize the air a little bit? They must, because everything can be magnetized. They're expanding and contracting and expanding and contracting, cutting through the air, okay, cutting through other matter if they're in a wall somewhere, okay. So in all likelihood, yeah, they're generating a very small amount of heat. At the end of the day, if the current's changing, and this is true, by the way, even if you're not in the world of AC, if I'm just starting, going like this, and I come to a stop, what do the magnetic fields do? They start collapsing. When I start up again, they start expanding again, stop. So even pulse DC, which is what your ignition system does, has the same problem, okay? It impedes the flow. So the power source is going to have to work harder to get the same amount of power out the other end. So now in the world of DC, if I want my 1 horsepower out at the saw to cut lumber, right, I'm going to have to put maybe 1.2 horsepower in at the generator. Particularly if the generator is like, you know, up there in wherever it is, San Onofre, San Clemente. Okay? Or I don't know where the nearest power plant is. Carlsbad. Right, in Cetus. So long, long ways away. All of that's inductance. So this imposition, what's it coming from? Isn't it coming from current? Didn't we already say that current creates heat? So it creates electromagnetic field that impedes, and it creates heat, which is a loss of energy. So current in both cases is kind of bad for long transmission of power. So the lower we can make the current, the higher the voltage, the better things are going to be with respect to this. So, and this note just says something, what I've already said multiple times. Hysteresis, or this delay in magnetic field, and then the subsequent collapsing, trying to keep the current going. It's constantly trying to prevent the change of flow. And if we get it in a true cyclical rhythm, that sinusoidal rhythm, where it's going kapoosh, kapoosh, back and forth, what's going to happen is it's going to not only is it going to impede, but it's actually going to cause a delay in the current buildup. So the voltage will go up, but the current will delay coming up. So now what's going to happen is instead of the voltage and the current coming up and going down, staying together, because of this impeding, the voltage is going to go up and then the current's going to start going up. And then they'll start acting out of phase with each other. So they'll be out of phase with each other. That could be a problem. However, it may be that this will benefit us. Because we've already said that capacitors sort of behave differently from inductors. Capacitors resist DC. They love AC. Inductors resist AC. They love DC. So maybe the two, where the two meet, we can take some advantages of this. We got to figure out some way of modeling that. But it may be that these two, we can use two of these to eliminate their respective effects. So I think I'm going to do one more slide, and then we're going to do our batteries and call it quits. Okay, so current made by the magnetic fields produces a counter motive force, creating an imposition or an impedance. I've now invented a new term, impedance. Okay, and somehow or another, this is reacting to the AC. Now, it occurs in a single wire, but it's not that much. It's a very small amount. But when I take that wire and make it into a coil, any kind of a coil, now all the magnetic lines of flux are cutting their respective partner wires, loops of the wire, really becomes significant. So this induced counter voltage creates an opposite force that delays and impedes the flow of the initial flow of current.
Like a step down?
Huh?
Like a step down or reduce? Do we do this one?
Don't try to visualize it that way. Just the only way I know of to visualize it is it acts like resistance, but it doesn't create heat. It doesn't cause the wire to be any hotter. It just says the magnetism is going to cause a delay, so I've got to work to carry that power through. Now, what the magnetic field is doing in terms of robbing that energy is probably heating up the surrounding atmosphere, because it's leaving the coil, it's going outside, coming back in. So if that coil is in a metal case, or it's in a plastic case, or it's in a big housing, whatever those magnetic fields are cutting through are now being magnetized as well. And so there's got to be a whole lot of eddy currents happening in them. So, and that's going to be converting into heat. But it won't be the wire getting hot. The wire will have its own getting hot issue that's resistive. But the loss of energy from inductive reactance will be just another value of units like resistance. Actually, I lied. There's a couple more slides. So, like I said, with respect to capacitance, the more the voltage changes, or the faster it starts going back and forth, the more this resist or this impedance occurs, the more it interferes. So if I have a fixed direct current, solid, 12 volts, 8 moving up, 8 moving down, Magnetic fields are stable, they're not going in and out. There's no counter motive force being produced. So this value of impedance goes to 0. And in a pure DC circuit, it still exists, it's just a value of 0. Right? High rate of change, whole bunch of impedance. No change at all, goes to 0. DC goes to 0. AC. Aircraft AC, 400 that goes, that's pretty significant. And we don't really get a sense of how much power all the lights in an airplane represent. It's a lot of power. So the little bitty brake light bulb in the back of your tail lights, if you haven't gone to LEDs, which many of you cars have, but original 1157, I kept saying 47, 1157 filament or bulb. That's about a 21 watt, 22 watts. Well, what's that, about 1.8 amps for one little bitty light bulb? Okay. Think about all the lights, the overhead lights and all the rest of the stuff in an airline. Okay. Now they've done some stuff to make them quite a bit more efficient, but that's a fair amount of amperage needing to drive all of that. In a cruise ship, how many light bulbs does a cruise ship have?
35.
I wonder what their light bulb budget is. Got to be a lot, right?
The generators.
They could do a lot to convert to LEDs, couldn't they? Yeah. Okay. So what's interesting about this is we can plug this in to some formulas. If we know what the total amount of inductance is, we know what the frequency is, we can come up with what that impedance value is. So we're going to need a term for what that is. Okay. So we're going to use a term called reactance. We're going to say this reactance, and then we're going to say it's reactance caused by inductors, or inductive reactance. And once we come up with that term, we can calculate what it is for a given load in a circuit. We can treat it just like resistance. We can assign it units of ohms, and we can apply Ohm's law to it. So we're going to call this inductive reactance, and we're going to say that in series circuits, where I've got inductive reactance, Ohm's law is going to apply. I can add the two loads together to get total. Okay? I cannot add it to resistance yet, because the way resistance acts is, we haven't got there yet. We've got to create a model on Descartes' coordinate system to show you how to do that. And I can say that as frequency changes, reactance is going to go up or down. And I can say, in Ohm's law, if I have two inductors in parallel, the total amount of reactance is going to be smaller, just like resistors. And I can use the 1 over formula. Okay, so I'm going to have to invent some symbols. Instead of R, we're going to have to say X sub L for reactance. Okay, and then using X sub L, we can then calculate some value of impedance for this in ohms, and we can apply that to Ohm's law. Okay, so it's a good place to stop. Next week, what we're going to do is we're going to start with capacitance, and we're going to find it also has reactance, but it plugs into Ohm's law differently.
Capacitors and capacitors are two different things, right?
Capacitors create capacitance. Okay, but so do light bulbs, so do lightning bolts, or not lightning bolts, discharge. anytime I have two states of charge next to each other, close to each other, there's a capacitive relationship between them.
Thank you.
All right, so go out and get one last measurement. Leave your power supplies turned off, the cables kind of buckled up a little bit. Voltmeters turned off. I'll clean up the hydrometers, leave the caps on and snug. I'll rinse the batteries off as well.